Billions of years ago, Mars was a vibrant, blue-green world. It was covered in vast oceans and thick air. Then its atmosphere stripped away, and the surface evaporated into a frozen, barren desert. To piece together exactly how that happened, NASA sent the Curiosity rover to Gale Crater. Its target is Mount Sharp, a massive peak rising 3 miles high right in the center of the crater basin. This diagram illustrates a geological rule called stratigraphy. Because sediment stacks over time, the bottom layers are the oldest, and the top layers are the youngest. As the rover climbs the mountain, it is literally driving forward through Martian history. Looking at this model of the rover's path, you can see it recently crossed a distinct boundary. It left behind the ancient water-rich clay layers and entered an upper zone packed with sulfates, salty minerals left behind as water evaporates. This marks the era when Mars supposedly dried out completely. Planetary scientists assumed this upper sulfate layer would hold a straightforward, desolate geological record of a dead world. But then, Curiosity rolled up to a winding rock formation known as the Amapari Marker Band. This rock band sits right in the middle of a geological dead zone. Its very presence here directly contradicts the accepted timeline of the planet's demise, forcing a complete rethink of how and when Mars lost its water. The evidence starts at a specific spot within the marker band called the Prow outcrop. Here, the bedrock is covered in parallel, repeating ridges that measure exactly 6 millimeters high. This diagram shows exactly how these structures form. They are symmetric wave ripples. You get them when wind drags across the surface of a shallow lake, pushing the water back and forth. That oscillating motion carves perfectly even peaks into the loose sediment below. Because the geometry of the ripples is directly tied to the energy of the waves above them, the exact 6 millimeter height gives us a precise measurement. The water that formed them could not have been deeper than 2 meters. Still looking at this wave model, there is a second highly restrictive requirement. If this lake had a layer of surface ice, the wind's energy would be completely blocked, and the sand would sit flat. To build these ripples, the water remained completely liquid and exposed to the open Martian air. These perfectly spaced ridges are the fossilized shores of an open-air lake. They prove liquid water was pooling on the surface millions of years into the era when Mars was thought to be a frozen, arid wasteland. The physical shape of the rocks tells one part of the story, but their chemistry reveals another. Curiosity carries an instrument called ChemCam, which fires a laser that vaporizes tiny patches of rock and reads the light from the resulting plasma to identify specific elements. This chart displays the chemical data pulled from those laser strikes. The baseline averages of iron, manganese, and zinc in Gale Crater are quite low, but inside the Amapari ripples, those numbers shattered the baseline, logging the highest concentrations of these 3 metals ever detected together in the bedrock. On Earth, when you find a lake bed loaded with this specific mix of metals, it is the result of reduction oxidation or redox reactions. This is a chemical process where atoms trade electrons, typically triggered by the interaction between liquid water and metallic minerals. This animated model shows why that chemistry is so important for astrobiology. Certain microbes on Earth don't rely on sunlight. Instead, they plug into the electrical gradient created by redox-active metals, using the chemical reactions as a biological battery. The Amapari Marker Band was a chemically hyperactive environment. Its dense metallic deposits formed a natural energy grid, providing the exact resources required to sustain microbial life on a dying world. To fully grasp the significance of these metallic ripples, we have to look at where they sit. This high-altitude terrain on Mount Sharp is incredibly steep and entirely dry, reflecting a deeply hostile climate. Yet right near the Amapari Marker Band sits the Geddes Vallis Channel. It's a deep snake-like cut in the mountain, filled with massive boulders, carved out by violent wet landslides rushing down from higher elevations. Combining the deep scars of Geddes Vallis with the delicate shores of Amapari reveals a much more chaotic history. Mars didn't dry out in a slow, steady, linear decline. As the global climate collapsed, water returned in sudden, episodic bursts, violently tearing through the rock before settling in craters below. The Amapari ponds were the quiet aftermath of those violent floods. They formed isolated, short-lived havens that concentrated liquid water and rich metallic energy into one place. The discovery of the Amapari Marker Band proves that habitable oases existed long after we thought Mars was dead. Because these specific, metal-enriched ripples provided the exact solvent and chemical energy microbes require to survive, they are now a prime target for future missions returning samples to Earth.